Okay, let's make a start. So some of you are moving into derivatives. In fact, probably both of you in this case would be moving into the derivatives related stuff. So I figured it'd be worthwhile to start sort of pulling that stuff ahead of our schedule. So last week we did a brief overview of the derivatives related stuff, some of the fundamentals there. Basically the idea of the derivative being an exploration into the gradient of any given function. So derivative specifically being the gradient of the original function for any possible value of x. In the example we had the quadratic x squared, you find the derivative of that, you get 2x. That is to say that for any value of x along that quadratic, substituting that into the derivative function, you get the gradient at that spot. Does anyone here need me to revisit the fundamentals in more detail, or should we get into the more like derivative techniques of like your chain rule, product rule, quotient rule type stuff? Cool. Okay. Because where we left off last time was with that chain rule related stuff. So to sort of bring that up again in a little bit. The way the chain rule works. So you will have a formula sheet for your exams and SACs that cover all of the key derivatives for the functions that are relevant. So you get your power functions, your exponentials, logarithms, sine, cos, tan. Those are the ones that will show up on your formula sheet. Technically, they'll show up a little bit differently to how I've got them here. They'll have these like coefficients of a involved with all those x's. What they've done there is an implementation of the chain rule, a simple implementation of the chain rule, but it is still chain rule nonetheless. When you would use chain rule is when you get a function that is not identical to exactly what you see on this table of derivatives here. So as soon as you have anything other than just x in these basic versions of the functions, you use chain rule. Or in other words, whenever you have a composite function. For instance, as soon as you have natural log of x squared, that is no longer just x. This is a composite function of x squared inside of natural log x. So in order to find the derivative of such a thing, technically there's a couple of ways you could do this, but treating it as a composite function, first things first, split up the composite function into its two parts. All right, so in this case, x squared will be its own function, and the natural log will be its other function. I'm going ahead and calling it g in this case. I think the textbook and the formula sheet uses u. I don't actually know why I use g specifically. It's just a variable, right? Just a substitution. Then, with those two functions, find the derivative of each. X squared will go to 2x, as per this part of our table of derivatives. And natural log will go to 1 over g, as per this part of the table of derivatives. From there, chain rule says the derivative of our function is going to be the product of the derivatives of each individual function. So you take this thing, you take that thing, multiply them together. What we're going to do from there, replace g with what it actually is and simplify the result. Final answer will be the derivative of the function that you started with. That's the gist of it there. Any questions on that procedure so far? That's where we left off the last review. Okay. I did mention there's another way of handling this one. This is going to be accurate to logarithms specifically. You could technically use your log laws here. So you could take this power of 2 out the front as a coefficient using the log law, and then because the coefficient's outside, now it looks like basic natural log x. So you can just do 2 times 1 over x, which sure enough gets us to the answer we would have had anyway. That's chain rule fundamentals. In the actual exam, specifically around the multi-choice section, what they'll tend to do is not just give you one chain rule, but they'll nest them inside of each other. Something like sine of natural log of x squared, something like that. typically they won't give you three separate known functions. One of them or multiple of them might be just generic f of x, g of x, h of x sort of thing, and you have to handle it from there using f dash, h dash, g dash as your notation for those derivatives. As for how you would handle it if they're all fully known, you're basically just going to repeat that substitution over and over again until you get it to its simplest spot. So basically, first identify the composite function. You got sine, you got log, you got x squared. The substitution that you make at the beginning should be the biggest possible substitution that you could make, so long as you get back to a basic function. So for instance, if I did a substitution for x squared, I would still have natural log inside of the sine. It wouldn't be as big of a substitution as possible. But if I take the entire bracket of the sine and make that my substitution, then that outer function does become just the basic sine, right? Sine x, sine g, same thing. But then you would go through here. So find derivative of that, pretty easy. That'll just go to cos. Sine goes to cos in that case. Finding the derivative of this is then itself another chain rule. We've just done this example already, right? Where you'd go through, make this thing the inner function, and then continue to do yet another chain rule. That becomes your derivative of g. We already had our derivative of the outer function. Once again, just finishing that up. Make the product of the two things, replace g with what it actually is. So they get a bit nasty, but fundamentally you're just making the biggest possible substitution that you can, and then continuing to go down the chain until you've created all the derivatives that you need for chain rule there. Let's do an example. Yeah, chain rule. So I'll get a screen grab of the chain rule specifically, the formula as well as the steps involved. Well, actually, at this point, it's worth highlighting. I do have an appendix here in the notes for this one specifically, which goes through literally all the possible combinations of chain rules. So here's all the power law related ones with a generic g of x function. Here's what you have if you have an exponential in there. What if you have a logarithm in there? What if you have a circular function in there? And so on and so forth. It's got literally all the combinations in there. So you can see both the generic outcome as well as the specific individual outcomes for all the different types of functions. Nice little lookup for it. But anyway, the overall procedure is screen grabbed in there. Let's see if we can apply it to at least one of the simpler examples. Let's go with 1a here. I believe that's what we did near the end of the last review. Gonna get the notes out real quick. Okay, so 1a says we're trying to differentiate x squared plus 1 all to the power of 4. X squared plus 1 all to the power of 4. First things first, we're going to realize that this is not an easy to spot function on our table of derivatives, which, now that I mention it, I shall have a screenshot of that as well for you to refer to. There's not an easy match directly to this, so we have to do a little bit of thinking to figure out, okay, this is going to be some sort of composite function. What kind of function is this closest to on our list? So I've got the actual function itself written out on the handwritten notes. A little bit blurry, but hopefully that'll focus. All right, that's a 2 there. Anyway, I've got the function written down. It's going to be closest to one of these derivative types. Which of those are we closest to? Or perhaps if you know further, what might we start doing to implement the chain rule here?
Set x squared plus 1 as the inner function.
That's right, yeah. Any reason why you specified x squared plus 1 as the inner?
It's fairly simple.
Sure.
Find the derivative of.
Yeah, yeah, okay. So you're setting um, what the second order thinking there is you've also identified that when you do that substitution, you get yet another simple function as well as a consequence. Like for instance, you wouldn't have just picked the x squared as part of it, or you wouldn't have tried to substitute anything else. You take basically the entire inner of the brackets there. But yeah, that's right. So we've done our substitution and now rewritten it in terms of that substitution. Nice. What else do we have to get done from here?
You can find the derivative of both the equations.
Yep. So let's go with the first one.
So
U
du by
dash.
dx equals to 2x.
Yep, that's going to be 2x using the first dot point on our table of derivatives. And what about y dash of u?
4u to the third.
Or u power 3 with the exact same rule, the first dot point there. Nice. We have those two derivatives. What do we do with them?
Multiply both of them.
Multiply both together. Yeah, that's right. These two multiply together. So our final y dash x, or let's see, did they use any notation for the question? They didn't actually use any notation for the function. You'll typically see things like y dash x, you'll see dy dx, anything like that. These are both the same, more or less. It's going to be the product of those two things. So 2x multiplied by 4u power 3. That's going to give us 8x u3 with one final step to figure out from here.
Substitution.
Substitution, that's right. So we had a u and an x in here. This is dy on dx. It has to be purely in terms of x. So we're going to go back, use that u equals x squared plus 1, back in that u spot. 8x bracket x squared plus 1, and yeah, power 3. Now, this is, yes, this is fully factorized. No need to expand it out and simplify from there. You can either do fully factorized or fully expanded as your final answer, of which this is factorized here. Just seeing a question come through. Are these docs from the calc section? Yes, they're from the calc section of the classroom. As far as the Unit 3-4 related classes, so Class 2, we have finished the functions relation stuff, yeah. The Unit 1 and 2 stuff is still going to have a bit of it going on. Like last time, for instance, we were doing the gallery of graphs, Chapter 4 for Unit 1 and 2 book. But okay, yeah, that's chain rule. So the only other one would be testing fundamentals as far as like question 8 here. So this is what I was sort of mentioning before, which is they might not give you actual functions here. They'll give you stuff like f and g. This is still chain rule applicable. You just got to know how to use them. And this is probably the more common way that it'll show up in your multi-choice. In tech-free, you'll do basically what you just did here. You'll have fully known functions. Tech-active multi-choice, they'll do this sort of stuff with f's and g's rather than actual known functions. So let's see how we handled that. It is still chain rule at the end of the day. We have h of x is equal to f of g of x. We have some additional information to help us out. We've got g of 3 is equal to 4. G dash of 3 is equal to 6. F dash of 4 is equal to 8. And our goal is to find h dash of 3, or in other words, the derivative of h with the x equals 3 substituted in. What are we going to do? I haven't explicitly shown how to handle it, but it is, we know it's going to be chain rule just based on where it is in the chapter. Would be worth asking at the beginning, either to yourself or out loud, why is chain rule relevant here? Because that'll help out by clarifying what you actually do.
Do we find the derivative of h of x,
Yes,
right?
so our goal is to find h dash of 3 eventually, of which finding h dash of x will get us there. You're right. So first goal, what's h dash of x? How are we going to achieve that?
We can use the chain rule, so f dash of g of x multiplied by g dash of x.
F dash g of x multiplied by g dash, did you say at the end?
Yeah,
Yeah,
g dash.
yeah. So just to break that up, basically we're still using the same idea as before. We're still grabbing the inner as its own little thing. So, you can say something like u equals g of x, derivative of that is therefore g dash x. Then you've now got h of g is f of g, and finally the h dash of g is equal to f dash g. So he's just sort of seen ahead and done the entire product at the end of those two things. So finally we had h dash x is now f dash g, where g was, just g. So g of x, and then multiplied by g dash of x. So it looks a bit nasty, but this is technically what you've done in the previous example, just with known functions. That gets us h dash of x. What are we going to do with that h dash? Ultimately, our goal is this, finding that.
We're substituting the values that are given us in our
Yeah, that's exactly it. We'll be using these values to help us out there. So firstly, just fundamentals, f of any value just means replacing every x with that value. H dash of 3 is no different, right? Just replacing, at least initially, every x is going to be replaced with a 3. So you're going to have f dash of g of 3 and then g dash of 3. We know some values of g of 3 and g dash of 3. So every g of 3 is a 4. So that's now going to be f dash of 4 in there. And every g dash of 3 is a 6. So that's now going to be a 6. And then finally from there, well, that's a bit blurry now. And then finally the f dash of 4 we know is 8. So now we got 8 by 6. These are the kinds of things I'll get you to do in tech active exams, which means you can use your calculator from that point onwards should you wish, although I don't know how much it would help so much, though you could substitute in, I guess, at this spot here, but you'd kind of have to be defining functions. The arithmetic isn't actually that challenging here. It's more about getting the rule. And can you still do this? I guess in the CAS, you can actually define g of x as just, maybe. Can you define g of x as just a generic function? Nah, probably not, actually. Yeah, I don't think the CAS is going to be too helpful for this sort of thing. So it's one of those things where even though it's tech active, you still need to be able to do your arithmetic by hand. I'll just be back in 1 second just so I can turn off the heater. It's actually getting quite hot. Okay. Could I please leave the working out? Yeah, sure. So that'll be there, basically. Had our original function, the known points. We wanted this thing. Step 1 was get our substitutions and derivatives right. Last up from there was the chain rule, and then subbing in the actual values itself. I'll leave that there for a bit. Okay. What else? That's the chain rule related stuff. Can we look at a specific question I'm struggling with? Yes, absolutely. You got it on hand, or is it a textbook thing you can point me to? Try to send it? Sure. Okay. Got it down? Awesome. I mean, we'll go through another a specific question here. I just got to receive it. Maybe while that's being sent, I'll introduce the next topic. That's going to be the product and quotient rules. So we've looked at how to handle composite functions at this point. The product and quotient rule are now here to handle what happens when you have a multiplication between two separate functions, or what happens when you have a division between two functions. Like for instance, if we look back at the screen share, one of them is x squared multiplied by sine x. This is not a composite function, it's a product of two functions. Composite function means you've shoved one function inside of another. There is no way to consider this a composite function. There's no way to have put one of them into the other. They're both separated by a multiplication sign. It's an invisible sign, but it's still there. And the other is the quotient rule. That's like really obvious to see. As soon as you see a division symbol in there, you've probably got a quotient rule related thing. It's very similar to chain rule in the sense that you just want to identify what's your v, what's your u, find the derivatives of each of those functions, and then put them into a special rule. So that's what the product rule one looks like, and this is what the quotient rule one looks like. Just quickly, I assume you'll cover limits and continuity in the 1-2 class. Once we go back to like where we're at specifically in the curriculum, I'll cover the limits and continuity. Well, actually, where is that? That might be at the end of this. Yeah, limits continuity is 9L, so it'll actually be a bit later. They do all the, which is a bit weird in Unit 3-4, because they even literally use, I think they use the limit stuff here. Yeah, they literally use limits at the beginning of the chapter and then don't actually discuss it until 9L. It's at the start of the course. Yeah, well, that's sort of the weirdness that I was just discussing here, which is they use limits, they introduce them here, but they don't actually tell you anything about them. So in the course that I've got written there, yeah, I thought it was a good idea to mention them ahead of time so you actually know how to use them when they come up in 9A. I think schools will typically do, they'll teach you the bare bones basics of limits just being a substitution, and that's it. And then you get more into detail at the 9L stuff. Yeah. Okay. Yeah, so this is just more rules. Question still hasn't come through. Let me know if it's something that I can pull up on my end. I do have like past exams and stuff like that I could potentially look through if that's a kind of question you've got. Otherwise, we'll just do some product rule and quotient rule practice. Let me look at. Oh, here we go. Keep getting false on the CAS and no answer when trying to do it. Sent it in the school. Oh, okay. Yeah, I'll probably just grab it from the school chat. Actually, no, I should be able to grab a copy here. Cool. Can I change the screen share to point at this instead? Does that show up any good? There's a lot of grey space there. Let me know if that's not readable for anyone, and I'll write out instead. Okay, so what are we doing here? We got function, which is a linear plus a circular function. Determine points where gradient is 0. Okay, well this should just be derivative equals 0. So let's see what goes wrong with that. So, gradient 0, remember derivative is the exploration into gradient. So by setting derivative equal to 0, you should be finding where gradient equals 0. I assume you tried that though, so let's see what you're seeing. define function equals 2x plus 3, oh sorry, just cos 3x. That domain might need to play a role. 2x plus cos 3x, derivative of h of x equals 0, comma x. You get the general solution. So that's a good sign, meaning we're seeing some actual values. From there was a domain of 0 to 2, pi over 2. So let's do that. 0 to x to pi over 2. That's going to get us these two exact values. We want 3 decimal places, so let's control enter on those. And then, yeah, sub in the actual points. So I'll walk through the full procedure at the very end. I just want to make sure I can get an answer first before I say things that aren't true. That'll be 1, and that one, so we do this one now. And that'll be the other. They have the same y value, which should make sense. We're looking at circular function related stuff. We would imagine the y values being more or less periodic in that way. Oh, wait, I just did the same point again. That's why it's the same y value. Nice. Yeah, okay, that's going to make more sense. That one, yeah, those are our 2 points. So that's the x, that's the y, that's the x, that's the y. Obviously using the decimal version of those for the actual coordinates you're given. But you were seeing false. Keep getting false on the CAS. Have I done anything different to what you were doing?
It doesn't seem to be.
Doesn't
I
seem to.
might have entered the question wrong.
Yeah,
I'm not sure.
potentially.
I've checked it multiple times.
Yeah, okay. Have you got it in degrees instead, maybe? I mean, that could give you some weirder results.
It might have been,
Might have been. Okay.
but why would it be false?
Yeah, that's right. Yeah, false. It shouldn't show false. It should show just weirder looking numbers for your x coordinate. Why false? Maybe. Yeah, what could be done? What could be done? Maybe if you still have the working out on your CAS, maybe send that as a photo and I'll look at that and see if there's a debugging issue. But basically, it seems like I've done more or less what you've done and it's just going to be a typo, right? So for everyone else, what I've done there is, first things first, we were told to find where's gradient 0. For gradient related stuff, you want to find derivative. So I've started by defining the function and then finding the derivative of that thing. For gradient 0, it means you want to set derivative to 0. So that's what I've done here. But what we got here was a general solution, which is pretty typical for circular functions because they go infinitely, right? So to circumvent that, just making sure we're putting a domain on there, the domain that was suggested in the actual question. That gives us our 2 x values, which I've converted to decimal over here, and then just basically substitute those back in to get the y coordinates of those spots, because we wanted to know the points, not just the x values, the full coordinate there. But yeah, I guess send your if you still have that working out, send it on the like send a photo of the CAS or something like that, and I'll see if I can spot a typo. Was there anything conceptually different about that, or for anyone else, should I clarify the procedure there? Cool. Let's get this screen share back to the book. Yep, that's the book. Good. So yeah, we were just introducing the product and quotient rule there. So we'll go through a quick example. Product rule, as I was saying, x squared times sine x. Right, these are two functions that are multiplied together, so we're going to use our product rule. So we want to assign one of the functions to v and the other function to u. With the product rule specifically, it doesn't actually matter which order you do it in. For those of you who have seen the formula sheet already, you might notice that I've swapped the order of the v and the u. That's not because it matters, it's more so because I want to build a bit more of a better habit. Because when you get to the quotient rule, the order does matter, and they start with v and u dash. So I figured I would try to build that habit a bit earlier. But fundamentally, it's multiplications and addition. You can do that in any order you want. So assign one of them to be v, assign the other to be u, or whatever variables you want to use. Find the derivatives of each using the table of derivatives, and then substitute them into the relevant spots. So you always do a cross, right? So original function multiplied by the derivative of the other function, and vice versa. A lot of the time, there's no real simplification to be done here, especially when there's different types of functions being multiplied together. The only time there's real simplification is when you have multiple polynomials multiplied together, because those can condense into each other quite nicely. Even if there's like sine and cos, those typically won't even condense into each other. Same with the logs. So a lot of the time you just plug it in and that's your answer. Same idea with the quotient rule. It's a lot more involved. There's subtractions now, so the order matters a lot. And there's a final division of v squared, which can be a bit of a pain. Oh yeah, I've seen the working out come through. I'll look at that, I guess, at the end of class, just so we can keep the pace on that. Well, actually, I've just seen, hang on, I think I saw something weird there. Solve sine 3x equals 213. Why did you make sine equal 213? Plot it manually. Yeah, okay. So you got a of x assigned. Oh, do you have a as the variable assigned to anything? Any like constant? No. Oh, cos looks like it's written out manually. Is it actually resolved into a circular function there? Something about that looks a bit weird.
I didn't get you what?
Because I'm gonna type out cos. Something about the way your cos looked seemed like it doesn't actually register as a trig function. If you just do ddx of a of x, do you actually get anything?
Check that. Yeah, I do.
Yeah, okay. Oh, wait, you're in degree mode and you're putting a 0 to pi over 2 domain. Yeah, that's why.
Oh, okay.
Yeah, okay, there it is. Fixed. Yeah, because pi over 2 as a degrees is like, you're looking at a fraction of a degree there. That's why there's no solutions. Cool. Anyway, quotient rule. Right, so the u and the v is going to come from the fraction itself. So numerator is always the u, denominator is always the v. As far as simplification steps, what you'll see in the actual textbook and even in the actual exam is it looks like shit and it's not great. So you might have denominators as big as that, if we're looking at the screen share. So your v squared is just that squared. That's both good news and bad news though. Good news is, instead of just writing all this, literally just write v squared up until the very end. Then sub it in. It'll save you a lot of writing out the same thing. The reason why you can do that is because having a large denominator like that with all these pluses separated means that the chances of it actually helping you with simplification is next to nothing. So you can get away with doing v squared until the very end because you can be safely assured that that won't actually be required for any simplification steps. You'll just leave it there. Pretty much anytime there's a plus separating things, it's going to be very hard for that to actually condense down. In the example I've given here, there's no plus involved. It's a very simple function. So yeah, sometimes you can actually get some simplification going on in there. Like for instance, you have a couple of x's as common factors, you can just take one out. But if you see like pretty much every example here, there's a plus, there's a plus, there's a plus, plus, minus, all these things are making it very hard for it to be an actual common factor in the numerator. So save yourself some time, just write v instead. Let's do at least one example of each. So I'll get I can actually screen grab the entire page, I suppose. Then you'll see a full end-to-end example of each. Product rule, quotient rule. Okay, let's do at least one of each. Where are we at now? This is product rule related stuff. Let's even jump down to like 6, where they're starting to use different functions. Shouldn't be harder, it's just gonna get you used to using more than just your power of x functions. Let's go with just 6a, I guess. X cubed cos x. Y equals x cubed cos x. And the goal is simply just to differentiate it. What are we going to do?
This looks simple enough. Do we need to separate this?
Yeah, so one of the rules that we've talked about are going to be relevant.
Oh yeah, the product group.
Product rule, correct. We've got x cubed multiplied by cos x, because there's a multiplication between it, product rule. Yeah, so separating it is just a matter of giving one of them the u and one of them the v. Doesn't actually matter which one we do. What do we do once we have those? Not like to focus today. I've got a screen grab as well in the chat to refer to if you like.
We can find the derivative of both of them, and then u dash v plus v dash u.
Oh yeah, yeah, you're right with the products there involved. Yeah. Hang on, I just saw a question come through. Mic isn't working. Oh yeah, that's no worries. No worries. Yeah, so derivatives of each. So x cubed, we've done those a fair few times. So that's just going to be 3x squared. I don't think we've done a circular function yet. What does cos differentiate to?
Negative sin x.
Negative sin x is correct, yeah. That one's directly on the sheet as well. So if I pull that up real quick, that's this one there. Cool. And then as for the actual product rule itself, yeah, so basically the dy on dx is going to be, and if you highlight your working out like I've done, you basically just multiply along the diagonals. So it'll be your u v dash plus v u dash. Using v's and u's can be a bit hard to see with my handwriting. I'll try to make it a bit more obvious. But yeah, just multiplying along those diagonals. So that's going to be negative x cubed sine x, negative x cubed sine x, and then plus 3x squared cos x. This is perfectly fine. It's fully expanded. If you really wanted to, you could take common factors of x squared out. And maybe there might be some possibilities with a different function where if you have like your sine plus cos, you might be able to use your trig identity stuff or like the Pythag theorem to do further simplifications if at all necessary, of which it is not necessary here, and in the vast majority of cases. Yeah, that's a basic product rule. Let's see if we can apply it to question. Let's go 5a. All right, this is where we're again trying to highlight how to handle these generic functions that are involved. So we're trying to find the derivative d on dx of e to the x f of x. Again, a generic function, not necessarily known what that is. What are we going to do?
Product rule again.
Product rule again, yeah, it's a product of two functions, and so for that reason we should use product rule. Separating them out, the u to the x, and then v can get the f of x. U dash, we haven't done an exponential today. What's the derivative of the exponential?
It's e to the x.
E to the x as well, yeah. Not necessarily required for any exam question. Do you know why the derivative of the exponential becomes itself? Does anyone know? The hint is that it's not. Oh, go ahead.
Um, we take the x, the derivative of the power down.
Yeah,
So yeah, the derivative of x is 1, so 1 e to the x is the same thing.
yeah, no, that is correct actually. Yeah, because what you're highlighting there is technically, chain rule is applicable in all cases. It's just that when you have x as itself, derivative that's always 1, so it doesn't actually ever play a role in your decision making. That's a good answer to that. The one I was specifically thinking of is more to do with what e actually is as a number, because this isn't actually true for any other base than e. I've just seen a question. Is the answer to e to the power of x times f of x plus f dash? Possibly. We'll get there in a minute. Just wanted to highlight this one thing real quick. Does anyone know where the e number actually comes from? It's more of a trivia thing than anything else, but it can be kind of helpful for your understanding of how the functions work. The e number is kind of like pi. It's irrational. Oh, you want to say something?
I was gonna say I think it's like one of those like it's like special constant numbers.
Yeah, it's one of the
Like
special constants.
2.7 something.
Yeah, yeah. Do you know what the relevance of it is?
I think it's like the only function that's like equal to its derivative.
Yes, exactly right. So basically, the idea behind it is if you choose e as a base of an exponential, the y value of any part on that graph is identical to the gradient at that point. That's why you have the natural logarithm or the exponential as a base of e usually. Its gradient is always equal to its y value at that spot. So this stands for a y value, this stands for a gradient value. They are the same thing, so they should also be the same thing. Yeah, nice. Like for instance, if you had a base of 2, what you'll find is your CAS will do, I think it'll chuck some logs in there. Let's see. d to the x of like 2 to the x, for instance. Yeah, you'll get like the natural log of the base involved, and the exponential will still stay the same. So there's a bit more to it. So this only works for bases of e, which you don't ever need to know how to handle any other base than e, but it's nice to know that little bit of trivia, because when you're working with exponentials, it might come in handy to know that relationship. But otherwise, yeah, nice. V dash is going to be f dash, and because it's product rule, we multiply across both. So we're going to now have, they didn't really give this a name, so feel free to use whatever notation you like. You're going to have e to the x f dash, and it's going to be plussed with e to the x f of x, which, yeah, does look like a lot like your answer. So it seems good, because what you did was you factorized it out. F dash x plus f of x. Yeah, nice. You can leave it in either of those forms, whether it's fully expanded or fully factorized. It's more so, I guess, whatever you think looks neatest. Sick. Okay, that's yeah, it's a product rule. Yeah, in the exam, they might do the same thing as before when we had to also submit a point or an x value afterwards, like they're doing it in question 8, actually. Weirdly enough, they also have 5b in here, which is e to the x divided by f of x. It's a bit weird because the quotient rule hasn't explicitly been discussed here yet. The reason... Does anyone know why this is solvable without the quotient rule? 5b. Again, it's more of like a higher level thinking thing.
Can we use indexes?
Yeah, correct. We can start using
negative index.
Exactly right.
F.
Yeah, if you wanted to, you could use negative indexes here because division and multiplication are basically the same thing. E to the x divided by f of x is the same thing as e to the x multiplied by 1 over x. And so for that reason, yeah, you can technically use product rule or quotient rule. I don't think I've ever seen it matter to understand that. I just thought it was worth highlighting, which I have an example here. And they did put it in the textbook, so I guess it's worth mentioning, but yeah. But for us, as far as we're concerned, the exam or SAC won't ever force you to use one or the other. If you know this is solvable with quotient rule, by all means, and you're probably better off using the quotient rule rather than trying to jerry-rig it into working with the product rule again. So let's give this one a crack. So you can solve it either way you like. How shall we start with this one?
We can use the quotient rule.
Yeah, quotient rule. So we've got to define our u's and our v's properly. Which one's going to go to which?
E to the x equals to e to the x and equals to f of x.
That's it, yeah. So that will be present in your formula sheet. You'll be able to identify it if you look back at the screen share by the fact that it's u over v. You'll see the u is definitely on top, the v is definitely on bottom. Actually, to make that super, super obvious, I'm literally going to pull up the formula sheet that you get so you can see exactly where it's going to be and exactly what it's going to look like. So there's your product rule, there's your quotient rule. It uses the dy dx notation. U over v. Cool, all right, we split them up. The next step is the same as the product rule, just finding the derivatives of each. And they're the same functions, so nothing really to be talked about there. What is going to be a bit different is how we actually now implement it. So what are we actually going to have written out?
The denominator is the derivative of the numerator minus the numerator multiplied by the derivative of the denominator. So
yes, I think you're doing this one
right?
multiplied together minus these two multiplied together and then dividing by that.
Yeah.
Yeah, cool. So again, if you write your working out, you'll notice the u and the v exact same as the working out for product rule. You still do it in exactly the same order. Just make sure you do your diagonals in the right order. So f times e to the x, whoops, minus this time with u times v dash. So e to the x f dash. And then also we saw that denominator, so f of x, is now squared. That's pretty much it. You can take a coefficient of, well, a common factor of e to the x out the front should you wish, but no need to. And even though that's f dash, it's not actually a factor of f of x, so there's no further simplifications involved there. Cool. That's pretty much it there. Product rule, quotient rule, very similar stuff going on. Okay. Question e to the power of x, f of x. Oh, yeah, you were answering the question. Let's see, did you get it? E to the x power of x times f divided by fx squared. Yes. Yeah, you had it right.
So I just typed it into some.
Yeah. No, I get you. All good. Yeah, cool. So that's going to be pretty much it for those related things. We do have some time left over, so with that in mind, We could do limits continuity. I'm just going to see if there's anything else that's worth touching on first. No, not really. Cool, let's do limits. I'll just pull up some notes for that. Okay, fundamentals, limits continuity. Okay. As far as your understanding of limits is required for methods, we don't need to do a whole lot of, you don't need to know it at the finest possible detail. You just really need to know it in the context of the differentiation by first principles, specifically in like your unit 1 and 2. You definitely want to be able to know how to do the fundamental way of doing the differentiation. That was what you're looking at in 9A in the Unit 1 and 2 book, all about taking those tangent lines, if you guys were here for the first time we discussed this. So what's the idea of limits? What's going on? The limit is basically an exploration into functions as they approach a specific point on the graph. That's pretty much it. So this notation here, in fact, maybe an easier one would be using an actual example. So for instance, the limit of f of x equals x squared as x approaches 0 just means what's going on the quadratic as x goes closer and closer to 0. Now, saying that we're going closer to a value is not necessarily the same thing as being at that value, mainly because getting closer to a thing implies a direction. You can come from the left-hand side or you can come from the right-hand side. In a decent number of functions, they are already continuous. They have no breaks involved, so that shouldn't matter. That shouldn't be any difference. All right, coming from the right-hand side should be the same as coming from the left-hand side. They both reach that turning point. That's what we mean by does the limit exist. The limit exists so long as if you come from the left, you get to the exact same point as if you had came from the right. And that is literally just a matter of you looking at the graph and tracing it with your eyes. There's nothing more to it than that. Get to the same point, the limit exists. Congratulations. If the limit exists, the value is whatever y value you end up at that particular point. So in this case, the limit exists and the value of the limit is 0 because the y value is 0 there. The reason why we use limits at all is because of asymptotes, specifically the vertical asymptotes, or actually no, even horizontal asymptotes. Any asymptotes in a graph is where you start using limits because we can't say what the value is here. And the reason why is because if you approach from the right-hand side, you're shooting off to like positive infinity. Coming from the left, negative infinity. It's diverging. They're getting further away from each other. Because they are tending towards two separate values, the limit is considered not to exist. That's probably the easiest example of a limit not existing. Technically speaking, this is also true for a truncus. A truncus would have both sides shooting off to positive infinity, but the nuance there is they don't actually consider infinity to be a value. It doesn't actually approach a specific value, it approaches infinity, and for that reason, they still say the limit does not exist. So anytime your graph is approaching an infinity of some sorts, even if it's coming to from the same directions, or at least headed towards like positive or negative in both ways, you still say it doesn't exist. That's maybe one of the more confusing bits of it. But the spark notes of that is just infinity just means limit doesn't exist. We'll keep it as simple as that. There's a whole bunch of properties as to how they work. You don't really need to know. Like this is stuff that you just kind of already do. Like how we work with derivatives, right? If there's coefficients there, we kind of just ignore them, do the arithmetic, and then chuck the coefficient in later. If we have pluses and minuses, we just do them individually and then add or subtract the results. Products, same thing. This is probably a bit more unique. Usually you can't do that with other functions. You can't do the product and split them up, nor can you do this power related thing. So limits do have a few more unique things you can do with them. I haven't seen any of it really come up though. This will be more so for people who have SACs or exams that, well, more so SACs, I guess, that just throw the kitchen sink at them. So it might be worth brushing up on how these all work. It's just basically how derivatives work, but with a few more things you can do. That's it, really. The most important part of the limit stuff is how you evaluate discrete limits. A discrete limit simply means that your x value is approaching a value, an actual specific value, not an infinity. That's all it is. And in this case, as far as methods is concerned, you're pretty much always going to be working with polynomials. And if the question is written correctly, it'll be working with polynomials that have a division where if you had just subbed in the value, you should get a divide by zero error. Because otherwise there's no point for a limit. Right, if you just sub in the value, you don't need a limit. So how do we handle this? If we sub in 2 directly, we're going to get that divide by zero error. What we do is we factorize and we try to cancel this out. This is what's referred to as a removable discontinuity. This has a potential for divide by zero, but if you factorize your numerator in such a way where you can cancel out that factor, you can get it down to 2x minus 1, and then you can sub in that value. So in reality, limits is really just algebra. It says limit here, but in reality it's just saying simplify this down until you can sub in the value of the limit. As far as interpreting this though, the limit is 3 in this case, because when you sub in x equals 2, you get y equals 3. However, the value of the function is still undefined. Even though you've gone through the effort of the algebra of simplifying this, x equals 2 is still not part of the domain. So here's the difference. The value of the function is undefined. The limit of the function is 3. What this would look like would be literally the graph of 2x minus 1 with a white dot. So I'll draw that out. Graph of 2x minus 1, and at x equals 2, you would have a white dot. That would be the x equals 2, and that would be y equals 3. It's invalid at that spot, but you can see that as coming from the right-hand side gets you to the same spot as having came from the left-hand side. The limit exists, its value is 3. The value of the function is still considered undefined. Those are the main things that will probably trip people up. So I should probably pause there. Any questions as to how that's working? Okay, cool. We don't have too much more time left, so I'll just briefly cover what the rest of this chapter would be considering. Sometimes you can set your limit to be infinity, in which case there are 3 key examples of what those things will always evaluate to. If you forget those shortcuts, it's fine. You also have a 2-step procedure that works in every case. We'll cover that at some point. You got 3 examples there. And then lastly is continuity. As far as you guys care, for the most part, at least being able to spot continuity, it just means that your line has no breaks in it. That's really it. As far as what the textbook is asking you when it says prove continuity or disprove continuity, it's talking about these 3 criteria here. So as long as you can prove that checkbox 1, checkbox 2, and checkbox 3 is met, your function is considered continuous at that spot. Again, we'll look at that in more detail in the actual lesson. Or if you feel like it, it's in the coursework as well, right at the beginning of the calculus chapter. And lastly, differentiability is a slight extension on to continuity. If your function is discontinuous, it's definitely not differentiable at that spot, but that's not necessarily true the other way around. That's where that's headed. There might still be a few lessons before we actually get there specifically, but actually we have a full house here, so I think we should just be able to pull up our curriculum to get to this spot anyway. I'll work on that in the background. Cool, alright, that's about it for today then. If there's any further questions, feel free to stay behind for a bit. Happy to chat. Otherwise, thanks for coming. I'll see you next time.
Thanks. Have a good day.
You too.
Chris, would you be able to send the curriculum for which specific chapters from your syllabus are covering each period?
And the curricula. I haven't written a class doc for this because it was technically a review class here. Because
Oh, no,
we're
not
ahead
just for this one, like just overall, like which chapters you're covering each session.
Yeah, that's in the I've got to rewrite the curriculum because we are ahead of schedule now. But
Yeah.
basically, it's in the what is it? The Mastermind Premium Unlocked modules. They have Class 1, Class 2, Class 3, and you'll see the modules that are relevant as well as the oh, actually, it is just modules, isn't it? Hang on, let me double check that real quick. Does it say? Oh, I think it says chapters. Let me see. Actually, pull that up on the screen share as well, so we can all see what's going on. Okay. So class 1 curriculum, we have a look. Yeah, so it's got the chapters that are relevant as well. So this will be the unit 1 and 2 thing, so we're doing very different things. Sorry, we're down here, aren't we? I went too far. So there's the gallery of graph stuff like chapter 4 for unit 1 and 2. The class 2 related stuff is going to be is that. So we're already, where are we up to? We've got till term 2, week 1 already. So I've got to basically bring all of this forward. So I guess for your purposes, maybe reading like these bits would be it, I suppose.
Okay.
Cool. You got the chapters there.
Yeah, because I think when we get back, obviously next week's the last week of school, so I think once we get back to school after holidays, we'll start on calc.
Oh, okay, so you guys haven't started calc just yet. Yeah, sure. No. That's fair. Yeah, so as I said, I'll pull this stuff ahead of schedule so we can catch up on it. Because next week is supposed to be a review week, but that just means you guys get to choose whatever, which is probably going to be derivatives. So we'll just bring this up.
Yeah.
Sick. All right, cool. I'll make this more. I'll rework this to make that happen.
Yep.
Easy.
Thanks, Chris.
Cheers. How's it going, Raquel? Got a question for me? Or?
No, sorry, thank you.
All good. All right, have a good one.